Captain Hassan, Electrical Unit Leader Frat, Mechanical Unit Leader Mahmoud, Mechanical Unit Member Izil, Sponsorship Unit Leader Ali Ozan, Software Unit Leader Talayane, Software Unit Member Aaron, Software Unit Member Jan. During the creation of our drone, we meticulously documented the entire process in a detailed Gantt chart. From the outset, we conducted thorough research to determine the most effective methods for constructing our drone. We devised a plan encompassing every stage, from conceptualization to design, fabrication, and beyond. In this chart, you'll find a comprehensive breakdown of our journey. From selecting the optimal motors to implementing image processing techniques, from training our pilots to the timeline for our test flights, every aspect of our project has been meticulously planned and organized, ensuring that each step aligns with our overarching goals for success. You are now seeing our latest design images. The batteries and drop mechanism on the first floor of our vehicle are positioned there to lower the center of gravity. On the second floor, we have 3D printed parts connecting the engines and the fuselage. On our second floor, where the motors are connected to the body, there are ESCs that we use to control the motors and the power distribution board that we use to provide power to them. The reason why they are positioned on the second floor is to protect the sensors located at the top from the magnetic field they will create. On our third and top floor, there is a camera, GPS, SIC radio, remote receiver, MAUC, Raspberry Pi 5, Jetson Nano and Cube Orange. These devices are positioned at the top for easy access and to avoid being affected by the magnetic field. We decided to craft the drone's body from carbon fiber for several reasons. First and foremost, it was crucial for us to maintain the lightweight nature of the product. Additionally, using carbon fiber allowed us to achieve a smooth and flat surface, which is essential for aerodynamics and overall performance. Now, let's delve into the materials and process we used to create the body. We utilized a combination of materials including MO8 PVC foam, TW303K carbon fiber, accelerator containing polypol 320 TA polyester resin, mold release agent Polywax and PVA, liquid Polywax PVA mold release agent, peeling fabric, vacuum blanket, vacuum nylon, and vacuum sealing compound. By layering these materials as seen on the screen, we were able to create a highly durable composite material. Instead of opting for a pre-made body, we chose to manufacture it as a team, which not only provided us with valuable experience but also ensured the durability and quality of the final product. Through this process, we achieved the desired strength, smoothness, color, and preserved the planned aerodynamic structure of the drone's body. This method allowed us to tailor the drone to our specific needs and preferences, ultimately enhancing our performance in the competition. When selecting the engine, the drone weight was planned to be 28 pounds. Additionally, the weight-to-thrust ratio was accepted as 2. Therefore, the thrust that our engine should produce is calculated as 52 pounds. Each of the coaxial U82 motors we chose produces 28 pounds of force. Our total coaxial force is 112 pounds. The reason we use a coaxial motor is that it consumes low energy while producing this force. We chose to design a quadcopter drone instead of a hexacopter for several reasons. Firstly, quadcopters are generally simpler in design and construction compared to hexacopters, resulting in lower production costs and easier maintenance. Additionally, quadcopters offer sufficient stability and maneuverability for our intended applications without the added complexity of additional motors and arms that come with hexacopters. Moreover, quadcopters are more widely used and researched, providing a larger pool of resources and support for troubleshooting and optimization. Overall, considering our requirements for simplicity, cost-effectiveness, and practicality, a quadcopter design best suited our needs. In addition, quadcopters allow for quick deployment and are generally more user-friendly, requiring less training and setup compared to fixed-wing alternatives. When selecting the drone's battery, the selection was made by taking into account the performance of the motors, the flight duration of the drone and the consumption of other electrical components. The voltage required to power the motors used was met by 12 LiPo batteries. While creating the battery pack, 6 6S batteries with a capacity of 10,000 mAh were used. These batteries were connected in pairs in series and then parallel to each other to create a package with a capacity of 30,000 mAh for 12s. With these values, the flight duration of the drone is calculated as approximately 35 minutes and is above the 30-minute mission duration. MSDS of the batteries were examined and stored under the necessary conditions. In this way, it will be possible to enter the competition area with healthy batteries and minimum risk. In addition, outside of the test, the battery packs were stored in specially produced LiPo bags. During the competition, the voltage values of the batteries will be read regularly by the sensor, and in case of abnormality, safety procedures will be activated. The voltage values of the batteries have been calculated to use 80% of the capacity of the LiPo batteries. In this case, it is possible to transport the batteries safely at the end of the mission. In order for the batteries to be noticed in case of an undesirable accident, the necessary markings were made on the batteries and fixed to the drone frame. The most optimal placement was chosen to avoid magnetic effects during the flight. Components that may show low efficiency due to electromagnetic effects are positioned in certain places on the frame of the drone. Additionally, the cables are wrapped with aluminum tape to minimize the electromagnetic effect. The Mate System brand's flight controller Hub 12S model will be used as the power distribution board, PDB, in the EagleClaws drone. The board weighs 21 grams and supports voltage up to 12s. It provides a continuous current of 70 A across 4 outputs and has a burst current rating of 110 A. It includes 5 volts to 12 volt spec modules to supply power to other components. The Mach brand's HS200HV model power module will be used in the EagleClaws drone. This module, with its built-in regulator, will provide the necessary power to the Orange Cube device and enable voltage and current readings from the batteries. The HS200HV module has a current sensing capability of up to 200 A and operates with supply voltages up to 14S. External BEC power is required for the sensor to operate. In this visual, you see the system elements and their connection diagram for the purpose of performing the task and for security purposes. In our pursuit of safe and efficient flight operations, we heavily rely on the gazebo simulation environment to anticipate and mitigate unforeseen challenges that may arise during actual missions. Gazebo serves as a cornerstone in our testing infrastructure, offering not only a secure environment but also a highly flexible platform for script execution and scenario simulation. At the heart of our simulation setup lies the seamless integration of multiple technologies. The AUVSI plugin plays a crucial role in this integration, providing the necessary connectivity with the gazebo driver to grant us precise control over the simulated environment. This integration ensures that our simulations closely mirror real-world conditions, allowing us to test and refine our systems with confidence. To implement and execute scripts effectively within our simulated environment, we rely on the DroneKit library, a powerful toolset compatible with the Python programming language. With DroneKit, we can develop and fine-tune scripts tailored to our specific needs, whether it's testing autonomous navigation algorithms or evaluating response strategies to various environmental factors. Our simulation setup lets us test a range of scenarios, preparing us for real-world challenges. By refining and optimizing scripts in simulation, we ensure our drone systems are ready and reliable for deployment. Three distinct models will be deployed on the Jetson Nano for object detection, UAV-8 for shape detection, MEANS for color detection, and UAV-8 again for letter recognition. Each model will be comprehensively evaluated based on its unique features and intended applications. While EagleClaws has been selected for shape detection, it's worth noting that recent research suggests V9 may offer superior performance in this regard. Nonetheless, EagleClaws excels in simultaneously detecting multiple objects and has been optimized for robust performance in high-demand scenarios. For color detection, the CMEANS algorithm has been favored. This approach involves clustering thresholded images with CMEANS to derive color codes, which are then identified using a trained model, facilitating accurate color detection. The EagleClaws model will once again be leveraged for letter recognition. Following the shape detection stage, letter detection will be conducted on thresholded images within the identified region of interest, ROI, enabling precise identification of letters within the scene. The dataset comprises over 10,000 images sourced from diverse repositories, including internet datasets, real-world photographs, and synthetic images. Notably, our labeling dataset is integrated to enhance its diversity and richness. The Raspberry Pi HQ camera has been selected for image acquisition due to its ability to capture high-resolution images suitable for detailed analysis and processing. When discussing the threshold, a thresholded grayscale image will be showcased, followed by the meticulous outlining and labeling of objects within these thresholded images, ensuring clear identification and delineation of each object of interest. When designing the drone's body, we opted for a 3-layered structure to provide ample space for component placement. We chose oval edges instead of sharp ones to manage airflow better and ensure a secure connection between the arms and the body. Our drop mechanism works with 2 servos. One servo causes the other servo to rise linearly. When the rising servo reaches the required position, it is lowered again by the other servo, and then it turns and cuts the rope to be dropped, performing the drop operation. In the system design, it was taken into consideration that the drop to be released was selectable and not complex. The LiDAR sensor we will be using in the competition is a Mini Plus model from the Benoit brand. The reason for choosing this model is that the sensor is easy to mount, and stands out for its small size and low power consumption. The sensor has an impressive operating range, capable of continuous measurement from 0.1 meters to 12 meters. Moreover, it provides very accurate results with an accuracy of plus or minus 5 centimeters in distance and 1% accuracy in distance. Mini Plus 5mm distance resolution and adjustable frame rate provide flexibility for different applications. There is also an ambient light resistance of up to 70 clucks and a wide temperature range operating from -20°C to 60°C for reliable operation in harsh environments. The design of this sophisticated sensor is lightweight and robust and offers IP65 protection against water and dust. The LED light source acquires precise data by looking at its surroundings with a central wavelength of 850 nanometers and a wide angular angle of 3.6 degrees. The Mini Plus offers energy efficiency with 5-volt supply voltage and 550 milliwatts of power consumption, while increasing portability with a weight of 11 grams. Furthermore, its UART communication layer and simple connection via TTL USB converter simplify the integration process. We flew a total of 20 times to get ready for this competition. 3 of those flights were with an empty drone, and the other 17 were with the drone fully loaded up. We were cruising at speeds of 15 to 20 meters per second during most of our flights, showing off our control skills. We didn't let the weather stop us either. Whether it was calm, a little breezy, or even windy, we were up there flying, and we made sure to fly up to heights of 25 to 30 meters, just like the competition rules asked. We practiced hard and managed to nail 3 flights that met all the competition requirements. In less than half an hour each time, we successfully dropped off our payload with precision. First, we looked at our drone's weight, size, and how it flies. Then, we thought about things like how high it needs to be to take off safely and how high it can go without breaking any rules. We also considered stuff like the weather and how it might affect our drone at different heights. We wanted to make sure our drone could handle any conditions it might fly in. After thinking about all of that, we came up with the perfect height for our drone to fly. We made sure it was safe, followed the rules, and would work well in any situation. In the end, figuring out the best height for a drone to fly was all about thinking carefully and making sure everything would work smoothly. We're excited to show off our drone skills in the competition. To determine the hover time of our drone, we utilized a simple yet crucial formula. By dividing the current that the battery can deliver in 1 minute by the motor required current, we were able to ascertain the duration our drone could hover in a stationary position. Our calculations began by considering several key factors. We meticulously assessed the weight of the drone, including both the drone's body and the battery. Additionally, we sourced data from datasheets to determine the current draw of each motor. With this information in hand, we computed the total current draw for all 4 motors. Subsequently, we determined that the current that the battery could deliver in 1 minute amounted to 1,440, while the motor required current equated to 40. Through this calculation, we deduced that our drone could hover for a remarkable 36 minutes, an impressive feat by any standard. However, it's essential to acknowledge that real-world scenarios often necessitate adjustments to theoretical calculations. Considering factors such as maneuvering, wind resistance, and pilot intervention, we conservatively estimated that the actual hover time would likely fall within the range of 33 to 35 minutes. EagleClaws.